Thank you for that introduction, Jeff. My name is Michael Sporer. I'm the Director of Marketing at MoSys, and the title of my presentation, Memories for Extreme Networking. So there were a number of topic suggestions for this talk, and in the course of presentation I'll be touching on all of them: latency challenges and solutions, bandwidth versus capacity challenges, on-chip versus off-chip. What does a memory system look like in terms of size, throughput, power, and energy? So here's the agenda. I'm going to give some background, talk about packet processing and the requirements there, look at next generation networking, and then header processing memories. So I started working at a place called the Memory Technology Center in 1990. We evaluated commodity memories for Hewlett-Packard. We assessed DRAM, non-volatile, and SRAM devices, things like storage cell technology, fabrication, packaging, and interface standards. DRAM was high capacity, and SRAM was either low power or fast. There were no application-specific or market-specific memories. Certainly there were specialty devices, but nothing targeting a particular market. Embedded memory was just emerging, and it was thought it was going to squeeze out discrete SRAM. For certain applications it did, but the SRAM market hasn't disappeared completely. A lot in the memory industry is either attributed to or blamed on finer process geometries. Everything on this page, for example. In fact, the industry is driven by a balance of market requirements and supplier cost reduction strategies. Market and cost drive everything, not technology. DRAM were slow unless they were designed to be fast, and there was a market for that fast DRAM. You could access banks quickly without worrying about restrictions, that is, until it became cheaper to introduce a TFAW timing restriction rather than design a better and more costly device. Compute market didn't care about this restriction, so it was easily accepted. We had soft error rates. At one point they were designed out until design margins were compromised to save die size. And in 1990, rowhammer was in the distant past, also having been designed out. So everything here on this page and many more items came into being because of cost and market acceptance. Technology advancement was merely the enabler. As far as interface goes, DRAM had a progression of ever-increasing bandwidth. So did SRAM, both moving from asynchronous to synchronous interfaces. But there were a number of innovative memory devices and architectures, some of them listed here. They were defined or developed, and some were produced. But ultimately, in the end, the high-volume, low-cost commodity DRAM always remained dominant. So you can't talk about memory technology without talking about the distinction between commodity and specialty memory markets. In the commodity DRAM space, the cost advantage is so great that applications are actually optimized for the memory. In the specialty memory market, the opposite is true. The memory is optimized for the application. Even so, a specialty memory device still needs to deliver a compelling performance advantage, or it will fail. Incremental differences that deliver small performance improvements typically have a disproportionately high cost and risk. So when you're doing a specialty memory, you've really got to go, hit for the home run. In the late 1990s, networking memories emerged. In SRAM, we had asynchronous go to flow through, ZBT, and all the other trademark versions of it. And then after that, to dual port QDR and Sigma Quad SRAMs that we still have today. Networking DRAM started with fast cycle RAM, followed by RLDRAM from a competing company, followed by LLDRAM from yet another group of competitors. Content addressable memories emerged as highly specialized hardware-based table search match engines for networking. And of course, embedded on-chip RAM is the ultimate specialty memories that can be customized to specific applications. Now let's talk about packet processing. Packet processing consists of two types of operations: buffering on the left, where the packet is parked, and header processing on the right, where decisions are made as to what to do with the packet. The buffer needs to hold the packet long enough for the decisions to be made, Or conversely, the decision needs to be made fast enough to not overflow the buffer. The two are symbiotic. They go hand in hand. Large packets, for example streaming, approach the data rate of the port and they define the maximum data rate of the buffer. Small packets, such as acknowledge, come quickly and define the maximum header processing rate. The packet processor needs to be designed to handle both cases, the large packets that are high bandwidth and the small packets that have a very high arrival rate. So now let's talk about packet processing rates. They've been increasing inversely proportional to the port rate. So at 10 gig, the arrival rate was 67 nanoseconds. And at 100 gig, the arrival rate increased tenfold to 6.7 nanoseconds. There is some relief on the horizon. With IPv6, the larger header size increases the maximum packet size. That reduces the maximum packet arrival rate. So the packet rate is still increasing when we get to 400 gig ports, but not so much as if we stayed with IPv4. So just remember 300 million packets per second. We're going to come back to that number later in the presentation. Other emerging standards are 25 gig, which look like it's going to be replacing 10 gig as a low-cost solution. 25 gig is the basis of the 100 gig standard, 100 gig is 4x25, and 50 gig ultimately will be a lower cost alternative than 40 gig. 40 gig is 4x10, and the 25 gig technology to build these high-speed SerDes is going to be more cost effective on a per bit basis. Both of these standards will support IPv4, and the packet rates are really not going to be dependent on IPv6 because we're already solving those higher packet rates in the IPv4 space. Here's more detail on packet header processing. Here we have a diagram of header processing that takes place through an ingress processor, a fabric and out and egress processor. This is a simple layer 2 and layer 3 switch. The light blue boxes are each the decision processes. The dark blue boxes are the different forwarding tables, and each table has one or more memory transactions associated with it. The pipeline belongs to the Trident 2 switch from Broadcom. The Trident 2 has up to 1.28 terabits per second of throughput. That's 128 10 gig SerDes, which can be put into a variety of configurations. It's a chip with 4 billion transistors, and it has 388 megabits of memory. These devices can be used to build single chip top-of-rack switches, or can be tied together through switch fabric to create large chassis switches. The ratio of buffer memory to table memory has to fulfill the requirement that the forwarding decision needs to be completed before the buffer overflows. So faster header processing goes hand in hand with smaller buffer requirements. Here's an example of a data center network from a Cisco presentation. They use both merchant and custom silicon to build these machines, both the top-of-rack as well as the chassis switches. Cisco implies the merchant silicon alone cannot do layer 3 over the whole network, hence the need for their custom silicon ASICs. The interesting thing about the hardware and the packet processors is both the merchant and the custom chips exclusively use only on-chip memory, and with this they can build quite large networks. Here you have a single chip that has the highest throughput, lowest latency, and it's scalable. So the question is, what's missing? In fact, quite a bit is missing. Classification, traffic management, and service level requirements, just to name a few. Data center networks may have thousands of table entries or even tens or hundreds of thousands, but carrier and service provider networks can have millions in comparison, an order of magnitude greater. These on-chip memories don't have the capacity required, and once you go off-chip, the latency goes way up, which in turn requires much longer buffer time. Just a comparison of two machines, in the 7508, the packet buffer is external DRAM. In the 7050, the packet buffer is on chip. Maximum buffer time in the 7508 is 100 milliseconds. The typical buffer time on the 7050 is probably much less than a single millisecond. But as the table says here, the maximum defined by the 5 megabyte shared capacity. So the chip has a large pool of memory for packet buffer, and it could be allocated dynamically on the fly to those ports that need the additional buffer capacity. So the 96 megabits of memory in the Triton II isn't equally divided among all the ports, but dynamically allocated on an as-needed basis. You can see there's way more than a tenfold difference in buffer capacity when you go off-chip, and there really is no middle ground between these two extremes. So let's talk about packet processing again, this time in a carrier network or edge router. The number of header processing applications has increased, the table sizes are larger, and the packet buffer in current implementations are based in commodity DRAM. If we compare two pieces of networking equipment and just look at the difference in the amount of silicon, the power consumption, the thermal density, and the design complexity between these two pieces of hardware, just to accomplish layer 4 traffic management, the differences are substantial. On the right, a Triton II base switch with on-chip memory. On the left, a line card from a core network switch. 4 switch ICs, each with 2 TCAMs attached, and 2 traffic manager chips, each with 16 DRAM. And the machine on the right has twice the throughput, the machine on the left. Now we'll take a look at just one of the traffic managers, the 88650 chip, which has the external packet buffer. So here's the traffic manager on the previous page. 200 gig line rate, 240 gig oversubscribed. That means 24 10 gig transceivers. With only 16 DRAM, I assume they're running at a maximum rate of 2133, which results in a 37% bandwidth over-provision. This over-provision is needed to turn the DRAM bus between reads and writes. 133 milliseconds of buffer capacity is more than required. However, the DRAM bandwidth dictates the number of DRAM, not the buffer capacity. With an option to connect an external lookup device and an external statistics repository, I plug all these numbers into a spreadsheet and I estimate its package is 45 millimeters on a side. So what's next after this chip? Typically, you double up to 400. But just following the transceiver trend from 10 to 25 gig, that could be a 2.5x increase, up to 500 gig. Whatever it is, it's certainly already architected and in design. So we're going to step one beyond that and look at what's the next one after. Call it the N+1 chip. We're going to assume an 800 gig throughput, 100 millisecond buffer, and 37% bandwidth over provision. We're first going to define the packet buffer solution, then determine what sort of header processing is possible. This 800 gig DDR4 based packet buffer requires 42 DRAM just to meet the bandwidth requirements. At arm's length, this isn't feasible. The nets are too long and the escape is too complex. But if it were feasible, the package would need to be 55 millimeters on an edge. And I ran out of room on this slide to draw in all the DRAM, so I left half of them off. Next, let's look at packet buffers based on 3D TSV based DRAM. Certain values are immaterial as long as you recognize that the same capability is available to either solution. So for example, I'll assume a layer density of 8 gigabit, and as long as both have access to the technology to build it, then it's a fair comparison. Stack height options are the same between the two, as is DRAM cycle time. Hybrid memory cube might have a slightly faster array, but also has greater complexity and latency through its logic layer, which offsets any advantage the faster array might have. You can see the analysis indicates these solutions are not optimum for 800 gig. And as has been common in the past, tailoring the application to the available memory makes sense here. The ideal solution is a packet processor that supports an integral number of 100 gig and 400 gig ports. And let's face it, 600 gig isn't fast enough. So the obvious solution is to look at a 1200 gig processor. So here's a 1200 gig packet buffer with HMC. The data path is 4825 gig transceivers. HMC with 80% efficient 25 gig transceivers means that there would be 64 of those. In total, 112 transceivers. This would require a package body size of 50 by 50, and there would be 300 extra pins available to hook up external stuff. 100 millisecond buffer requirement dictates 128 gigabits. That'd be 2 stacks of 64 gigabit each, or 2 8-high stacks. This would be 2 cubes with 32 lanes each, and in the HMC specification available today, there is a package 16 by 19 available for that configuration. So we'll just assume same package available for these 25 gig parts. Serial links ease routing, and it reduces the thermal density by moving the memory off the package. In comparison, here's a 1200 gig packet buffer with HBM. Same data path, 4825 gig SerDes. HBM would be required to run at 1.7 gigabits per second per pin, and as we heard, that's right in the sweet spot of performance for this device. This also includes the 37% over provision to turn the bus around. The device is going to have some headroom, up to 2 terabits per second per pin, or maybe 2 gigabits per second per pin, or maybe higher. In any event, that supports oversubscription of the data path. Now, assume the packet processor, a 1200 gig packet processor, is going to be a reticle buster as far as die size goes. So we're going to assume maximum die size for the ASIC or ASSP, and that implies a maximum silicon interposer size. Maximum silicon interposer size dictates a body size of 45 by 45, and with that you're going to have about 400 pins unused available on the package to hook up other stuff externally. 100 millisecond buffer capacity is the same, 128 gigabit. That's 2 stacks of 8-high each. As mentioned before, the DDR4 option is not viable, but shown here for comparison. The board area consumed between the 3 solutions shows the 3D TSV base have a substantial advantage. Both have the same data path and the same packet rate. So just recall, the packet buffer is defined by the throughput. Reducing the header processing complexity doesn't reduce the packet buffer throughput requirement. Header processing, on the other hand, can have a whole range of configurations, from your simple layer 2, layer 3 capabilities that are needed for a data center, up to the carrier and service provider, more complex operations already described. So we're putting a lot on this chip, and a lot of configuration on this chip as well. So that a lot of functionality means a lot of power consumption. One of the dilemmas we have is how can we reduce the power consumption on the packet processor without reducing its throughput? One answer is to take the high power PHY that's on the ASIC and move it off chip. So we're going to put very short reach PHY on the packet processor itself and connect up to gearbox or retimers off chip. Not only does this reduce the power consumption on the packet processor itself, but it gives a whole range of configuration options to the OEM building the machine. One other thing, if you're going to connect this next generation processor up to 10 gig links, you're going to need an MLG gearbox. So even if you had a PHY on the ASIC that could drive a backplane or could drive all the way across a board, you're still going to have a gearbox in there anyway to connect up to the most prevalent link available in the industry today. So let's look at memories for header processing. Different applications have different lookup requirements. Sorry for the eye chart, but in essence we have between 18 and 26 memory transactions per packet for a carrier network. Let's assume half of those can be done on chip. That still leaves a typical of 12 transactions per packet, times the aggregate packet rate of 900 million per second. That gives us 11 billion memory transactions per second for the off-chip memory. And that doesn't include the searches. Searches could be a longest prefix match, an ACL, or some other type, but there are a few of those per packet, and the search table can be larger than what fits on chip. So we have here a proposal how are we going to solve the header processing with the HMC solution. Again, 900 million packets per second. We're going to support the small tables with the on-chip memory. You know, one of the things we can look at is putting memory on the package. You know, you put header processing memory on the package, and all of a sudden you run into a situation where each configuration is a custom package and a custom memory. It may or may not require silicon interposer. So if you're thinking, oh, that HMC, it's got a cost advantage because it doesn't require silicon interposer, well, that goes out the window as soon as you add these external memories. Remember also that high transaction rate memory is much higher power than buffer memory. Buffer memory can burst, stay in page, that sort of stuff. High transaction memory with its high random access rate is typically a higher power device than your buffer memory. So this package, it does have 300 pins to go external. You could add more data path for oversubscription. If you add more data path, though, you need to add more buffer memory. And the buffer memory here is external HMC. So for 12 additional lanes of data path, you need to add 16 lanes for HMC, and that fully consumes those 300 unused I/O pins. Other options for connecting up off-package memories, remember, they got to cycle at 900 million packets per second. Parallel memories, there just aren't enough pins to cover that kind of transaction rate, even if the devices were fast enough. You know, serial TCAMs, sure, you can hook up some serial TCAMs on those transceivers if you're not using them for oversubscription or HMC. Bandwidth engine devices, yeah, you can use transceivers to hook up those devices as well. Gives you a nice unified memory solution, gives you plenty of transaction rate to address the needs of this network. But the off-package memories, they compete with the oversubscription data path and the oversubscription buffer. The off-package memories, they add board area and more pins. If you needed more pins to do more stuff off-package, then now you're looking at a larger and more expensive host package. So the header processing solution for HMC is not entirely obvious. Nothing sticks out as the best solution, and the flexibility to reconfigure the header processing comes with a cost. Adding external memories adds board area, and they're already disadvantaged compared to the HBM solution. Adding package pins makes the package larger and increases the board area again. Nothing here seems easy or obvious. So now let's take a look at the 1200 gig HBM based buffer packet processor. Everything here is the same, 900 megabits, 900 million packets per second. With the small tables supported on chip, this package has 400 unused I/O pins. You can add more data path for oversubscription. And with the bandwidth headroom in HBM, you can support that without any additional buffer memories. You can add parallel memories. For example, a Sigma Quad SRAM. If you need the fastest possible random transaction rate, you might want to hook up a Sigma Quad SRAM to this device. But predominantly, you're going to use those unused I/O pins for serial memories. They could be serial TCAMs for search, or again, they could be MoSys bandwidth engines. It's a unified memory solution, covers search, lookup, metering, and statistics. A very high transaction rate solution. Just remember, the transceivers are a fungible resource, and the parallel pins are not. Once you dedicate pins to parallel, they're a fixed functionality, whereas the transceivers can be used for a whole variety of different stuff. So the solution that I'm looking at resembles this. Here we have a 1.2 terabit per second line rate packet processor. Supports oversubscription, scalable up to carrier class functionality. First, we have a reasonable package size, built with silicon interposer. I'm showing here an embedded interposer technology that Intel Foundry announced at the last Intel Developer Forum. Seems to be a lot of opportunity to take cost out of these advanced packages. This is plenty of VSR transceivers for data path, connecting up to MoSys retimers or MLG gearboxes, which support line card, backplane, and optical module applications. For header processing, the MoSys bandwidth engine and Sigma Quad SRAM, both of these are multi-sourced. And there are still pins left over to connect either additional devices like more bandwidth engines or additional data path. Regardless of the header processing or data path configuration, the packet buffer is a constant, so only one package configuration meets a wide range of applications. For those of you that are not aware, MoSys is a fabless IC manufacturer making high-performance, serial-attached intelligent memory devices for the wired networking market. We're in production with our second-generation device, and the time frame we're discussing here will have our third-generation device as well as a Sigma Quad 4 SRAM. The table here compares the device attributes, and the bullet lists are common to all three devices. The one thing I might highlight is the transaction rate requirements that need to exceed the aggregate packet rate of 900 million packets per second. And the random cycle time needs to exceed the packet arrival rate of the fastest port supported. So that's 300 million packets per second for a 400 gig port. All these devices are available from GSI Technology through a mutual second source agreement. Bandwidth Engine 3 targets three main application spaces. The device attributes are in the bullet list. And the application spaces are a high read rate lookup with up to 6 billion reads per second, a small single-chip high-performance buffer up to 400 gigabits per second, full duplex read-write data, intelligent offload of metering and statistics using single-cycle atomic read-modify-write macros. And we can implement various search functions using algorithmic-based multi-cycle macros. A little more about offload acceleration. When you use the on-chip functionality, the macros can be saturated with instructions using a narrower interface than if you were simply performing memory operations, saving pins and power. In addition, by offloading the host, you're saving those memory transactions that equals both higher performance and higher energy efficiency. We're moving the processing closer to the data, just like everyone here is talking about. Bandwidth Engine 3 is not just limited to this 1.2 terabit per second system. In fact, if two Bandwidth Engine 3 supports 1.2 terabits, one Bandwidth Engine 3 can support 600 gig or 400 gig easily. It also has two access ports that can be split between two host devices, as shown here. Using onboard intelligence, we can reduce the interface to only 4 lanes and still support these high processing rates. So we have a wide range of applications addressed by Bandwidth Engine 3, from mainstream 200 gig and 400 gig next year to high-end processors out in the future. So MoSys is delivering the Bandwidth Engine product family with offload acceleration and the highest transaction rate and data throughput in a single chip. We have a line speed data path ICs, highest performance per watt in the industry. Everything we do is focused on carrier class customers, and we deliver power, footprint, and economic advantages to our customers. And in conclusion, let's review the suggested topics. So, latency challenges and solutions? Well, today it's no longer about latency. Transaction rate is the new key metric. Bandwidth versus capacity challenges? So advanced packaging such as HBM or HMC enables DRAM to scale beyond monolithic DDR4 devices. On-chip versus off-chip? Each is needed depending on the application. And what does a memory system look like? Well, just remember, technology may enable the size, the throughput, the power, and the energy, but it's engineering that determines the configurability, the efficiency, and the cost effectiveness. So that's my presentation for today. Thank you for attending, and I'll be taking any questions you might have.